to this lecture. And here we're going to design a gusset plate and all the connection to it. Take a look at the problem we have. We got this, it's a bridge truss, and in the top corner of the joints where we have the top chord, and then we have the two member coming into it, we're going to design the gusset plate, the connection for that joint right there, which basically is the gusset plate going over here, and the bolt pattern connection, and for all members. Again, because this is a truss, we're going to do a shear connection. And as you can see, what we have, the loads are given, dead load and live load, they're both 24 kips each. And then the member tension and compression basically all been calculated, the internal forces. You have compression coming this way. On the top member is the compression. You got 262 on both one side coming in, and on the other side you got 345 kips coming in. Bottom member again is in compression, it's 102 kips, and this member is in tension and 113 kips. And we're going to go ahead and design the gusset plate and all the connection. We're going to use AISC latest edition, which is a 16 edition. So why don't you come with me? I want to show you something. One of the things you have to consider when you design a gusset plate is make it really look nice, because in this situation our gusset plate is going to be seen by the public, and have some architecture in it. And what you got to do really, try to line up with this edge and line up with this edge, and then make a nice trim over here. How big and how wide your gusset plate is going to be all determined based on what is the internal forces that it's in these three members, and how long, what does it take for us to make the shear connection. Remember, this is a truss, and our gusset plate is going to be a pin connection or shear connection. So what is the required shear connection? How many bolts I need this way, how many bolts this way, and how many bolts that way? That will tell me how big my gusset plate is going to be. And so if I have something like this, a gusset plate, I'm going to go ahead line up with this edge of this W shape right here, and then line up with this W shape, and then make a nice clean cut over here so it kind of looks nice. And how big it's going to be, again, based on how many bolts I need to make the complete the shear connection, and that's based on analysis, which we're going to do in a minute. Again, if you are a beginner, this is a W shape. We're going to make a shear connection with the top flange. Just put a bolt in here, and then we have another one on the bottom side that's the basic duplicate of this one. All right, let's go back inside and look at the... Okay, so let's start. We're going to use AISC 16 version, which is the latest one just put out last year. And then this is our top chord, this is the web member, and let's get all the information about this before we proceed. We're going to go to the book, and from table 2.4 and 2.5, ASTM A992, the steel is a 50 KSI, and ultimate load is a 65 KSI. And then ASC table 1.1 for W for the top chord, the D is 14.3, BF is 14.6, and TF is 0.86. And then for W14 is the same, those number down here. Also, we're going to go to a table J3.3 because we're going to use 1-inch diameter hole right here. When we're going to put the gusset, we're going to use a 1-inch diameter hole, whatever how many it's going to take. 1-inch diameter bolt. And then based on this table, the hole size is going to be 1 1/8, again 1/8 larger, which is pretty good. And you don't want to go smaller because I worked in the field when we had to put these things together. It really pays off if your hole is just a little larger to make them fit perfectly. So just write this down because I'm going to erase it. We're going to go ahead and continue with. Okay, so this calculation is going to take over some time. So take it easy. Get yourself a cup of coffee or a popcorn, whatever. Enjoy it. Again, last year we used this 15th edition, and there are some changes for a 16th version. So we're going to use the 16th version, which is the latest one. And one of the first things we want to do, because of what this load is given to us, let's calculate the required strength. Both, we're going to use both methods of design, load resistant factor design and allowable stress design. If you don't know what those two are, go on my channel. I have a video, what is the difference between them and why we use this or that. Story for another day. So we're going to go ahead and calculate the strength of this load based on these two type of design. So let's get to work here. And first we're going to go ahead and do that. And we have a dead load of 24 kips and a live load of 24 kips. And we're going to go ahead and calculate the, we got a top, this is a top chord. We got the left strength coming in, load coming in, and also right one coming in. So let's going to say left top chord, left top chord, which is basically this one right here, and PU, ultimate load, is equal 1.2 times 262 plus 1.6 times 262. Why is that? Because take a look at what I have on the screen. I was lazy, I just didn't want to put both load right here. What I have on the screen, we have one for dead load and we have one for live load. And based on AISC chapter 2, we gonna calculate the load combination. And you can see that also on the screen. So that's where this number comes from. 374 kips. So that was now the right top chord. So I'm going to say right top chord, RTC. This side, which is basically this load, and PU is equal 1.2 times 345 plus 1.6 times 345, and that gives 966 kips. Let's say kips for K. Now we're going to calculate the vertical web. Vertical web PU is equal 1.2102 plus 1.6 times 102, 286 kips. Then we have the diagonal coming in. Diagonal web PU is equal 1.2 times 113 plus 1.6 times 113, and that gave me 316 kips. Okay, so we're going to go ahead and do allowable stress design. The allowable stress design is load combination, just add them. So it's going to be PA is equal 262 plus 262 plus 262, and that is equal 524 kips. And for RTCD, it's going to become PA is equal basically 345 plus 345 for the right side. And that is 690 kips. Vertical web, VB, let's call it. PA is equal 102 plus 102, that's 204 kips, and diagonal web is equal 113 plus 113, that is 226. I don't know where I got that number. Okay, so that's our load calculation for both of them. Now let's do some structural analysis. Because remember in the kindergarten, when you just took structural analysis, we look at the member here. This member is, if I look at this one right here, that'd be 11 and 12. Okay? Because this is a pin, summation f of y should come out equal 0. And summation f of x should become 0. Remember those days? Those two should come out 0. So we can go ahead and look at this and do a structural analysis, see if this is going to work out really. We have all the numbers, so they're all the same anyway. Summation f of x is equal to 0. So we have 262 going the right way, minus 345, and then plus 113 times 12 divided by 16.28. This is almost equal to 0. It's quite, so that's good. Let's satisfy that. What about this one? Summation f of y is equal to 0. And we have plus 102 minus 24 minus 113 times 11 divided by 1628. And 113. Okay, I get 1.6 kips. So do this. What happened if you're designing this and somebody gave you this, make sure you double check all this number to make sure it comes out okay. And if that doesn't work out, ask question, why is it not happening? Because there are other external load right here. They did not include it in this calculation, or they didn't tell you, they didn't show it here, and that's why it's a difference. So they should show those external load, what is it, and how they come up with those numbers. And again, we take their word for it, but say that's okay, it's not much different. So the designer said there are some other external load which is not shown. Okay, fine. And now we have the load. We're going to go ahead and move on to the next stage. Okay, I'm going to erase this board, but while I erase this board, I want you to remember there are 3 things to make you happy. Number 1 is to stop thinking about the past and regret the past. There's nothing you can do about it. It's gone. So don't think about it and let it bother you. Learn from it. Don't forget it, and make something better out of it. Now we're done with the load calculation. We're going to go ahead and look at the bolt, what kind of bolt we're going to use on our gusset plate. Remember I showed you the gusset plate is going to be on top of this right here. And because it's a bearing tab, you're going to have the slippage. So therefore, we're going to go into section J3.9A, page 16.1142. Open up that page. It's right here on your 16, and this is the page. I don't know how much you can see. I tried to put it on. So read the first paragraph right there. It says when we have 2 surfaces you want to put on top of each other, you want to use a bolt resistant, slip resistant bolt. So that's what we're going to do. And from there we're going to write some stuff down. Phi is equal 1 for load resistant factor design. Omega is equal 1.5. Mu is equal 0.3 for class A surface. The du is equal 113. HF is equal 1. No flare is provided. Then we go to table J3.1. It's on page 116.136. In that table, which I got on table right here, hopefully, you're going to pick out our TB become 51 for 1-inch bolt, and then NS is number of a slipper plane, which is equal 1. Once we have that, and from this page again, we're going to go to this equation. It says right here, if you read that at the bottom, it says the strength of the bolt available for slip resistance is given by this equation. So let's write that equation down. I didn't finish it. And that's Rn is equal, this was 0.3 time du was 1.13, if I got that right, and then time 1, then time 51, and time 1. This is 1, that's 1, that's great. So our Rn is equal 17.3 kip per bolts. Okay, so this is available slip resistance capacity. Okay, that's available slip resistance capacity, that much kip per bolt. So let's come back in here, go back this way and this way from here on. Let me use a different color. I don't know which color shows up better, but I'll try blue. So we're going to have phi time Rn, and that is phi came out to be 1 times 17.3. That's a 17.3, and that's a kip per bolt. Kip per bolt. Over here we have Rn divided by omega, which is 17.3 divided by 1.5. So that is equal 11.5 kip per bolt. Okay, so now we have that. We calculate this, or go to table 7.3, which is in this book, page of 7-24. Let me double check that. 7-24. Go there, and then you look at the first line right here, all the way for TB is equal 51, and you end up with this 2 number also. So why we doing it both ways is always you as a designer do it both way. That way you're sure you have this, and you from the table you also got the same number, and then you feel good about it. Okay, before we go on, remember I wrote down these right here. We calculated this load at the early, so I want to bring this back up here. These coming back to the joint itself. We said, okay, this member on the right, coming in is a compression. This top chord is in compression. Compression is negative, tension is positive. So this member coming in a compression on the right was minus, so become minus 966. Here become minus 734. And then the bottom also is in a compression. It comes out to minus 286, which we calculated vertical right here. And diagonal is in tension, which is 316. And if we break down to an X component and Y component, 233 and 214, that's in load resistant factor design. So we're going to do the same thing in allowable stress design. And this is the same diagram, bang, 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 and you know what I'm talking about. So keep that in your mind. I will try to draw it on my notebook and put it back in here. I'm going to erase this, so we're going to continue. That way I know when I say, oh, this plus this or this minus this, you know where they come from. Okay, you got it? Good. You're doing good, and we're doing good. Take your time. We got plenty of time to go. Individual, just look at the RFID for now. The tension in this member is 316 kips. So I want to know how many bolts on both sides of the flange, when I put the plate on top of it, requires to satisfy this load. Same thing for here, and that's a 286 compression. How many bolts I need? When I get up here, we will talk about it again, but I just want to say while this is on the board, this is a continuous member. But what is required for this joint? It has to be the difference between these two, because one is coming this way, one is coming that way. It's going to be 966 minus 734. It's going to be like 200 and change. We'll get to that. Anyway, let me erase this board, and then we're going to find out how many bolts we're going to need on this one. We're going to start with this diagonal one first, and then work on the other one. So in here, for this member, PU was equal 316. And then we had the N required, number of bolts required. It's going to be PU divided by phi times Rn, which we calculated. I erased it. And PU was 316. And I believe the 50, this number here is 17.3. We calculated two different ways, using table 7.3, and then we also calculated. And so that gives us about 18.3 bolts. Now let's do the same thing in our process design. PA was, I forgot to write it down, was 226. 226 kips, and then N required is equal PA divided by Rn, or this would be time omega actually, if you do it right, which was Rn divided by omega, so I just put it on top. So PA is no, let's do that correctly. Remember we did it Rn divided by N, and this was 226 divided by 11.5, and that gave us 19.7 bolts. And you can see the difference between two designs. One is more conservative, the old-fashioned one. The new one is just less, more aggressive. But it's like 1 or 2 bolts. Pay attention here. This right here is one member, just like I showed you outside when I went over there. So this member are going to have 2 gusset plates, one on this side, one on back side of it. So now we have 2 gusset plates, right? And so the amount of bolt is just for this one member. That means it's for both gusset plate. And also we're going to have 2 lines, 1, 2, you know. We're going to have a 2 line. So let me write this down. For 2 lines of bolts on both sides, okay? That's where we're gonna fit. And this was a 18.3 divided by 2 side, 2 line. One on this side, one on the other side, both sides, so 2 line. So that will give us 4.58. So use 5 row. And if you know the spec, at minimum of 3-inch spacing. If you look at the table where we have the bolt, they usually give you 3-inch spacing. All right, in here, same thing. We have 19.7 divided by 2 times 2. That give me 4.93. same thing, use 5 row. So using both design, we end up using 5 row. So let's come over here. There's 1 right here. There's 2. There's 3. There's 4. There's 5. 1, 2, 3, 4, 5. Now we know our gusset plate in here, how far it's going to go to cover this area. Okay, so now we have 1, 2, 3, 4 space right here. From here to here, we got 4 times 3 is equal 12 inch. And normally, you can look it up and tell me right in the comment below. The edge distance we like to here from the center to here likes to be 2 inches. So therefore, the edge distance from here to here also to end of this plate is going to be 2 inches. So technically, if this doesn't control, the edge of my plate, one of the gusset plates is going to be like this. Remember the head cut I had? It's going to be like this, and then go up straight, and then go up that way. But we'll find out how many bolts we need here. Do we have to end up go beyond this point for how big our gusset plate is? So we know right here is the limit of our gusset plate right here. We're going to make a cut right there. And then we're going to go up that way, and then we're going to go this way. Let's see if this will hold, this idea of gusset plate. But we've got to find out how many we need here or how many we need there. Okay, so we got to find out, the next thing I want to find out, this gusset plate I'm going to use, how thick it's supposed to be. Let me erase this, we get to that. So the next thing we're going to work on this, let's go to a table, figure 9.1, page 9.4, 16th edition, open up your manual. And we're going to go ahead and find the LW of a Whitmore section. And Whitmore section, the only explanation I can explain is down, the red, really the down bottom here. So from there, LW is given. LW is gauge plus 2 times L tangent 30. So if I calculate that, LW is equal. Okay, so the gauge, a good rule of thumb is like the distance between here, we want to be 3 times the diameter of the bolt, which we said was 3 times 1 is 3 inches. And also 1.5 to 2 for the edge distance, which we used 2, which is the 2 inches. So we use 2 times of diameter on both. So if we use the same thing here and the same thing there, remember we covered this in when we at beginning we went over connection bolt design. So now you do the math, you're going to have 2 inch and 2 inch to the center, and then you got 10 inches. If you can fit 5.5 inch, that'd be great. So that's what we're going to do. We're going to make this to a 5.5 inches. So you got 5.5 inches, and then you got 5.5. So from here to here is 2.5, and from here is a 2.5. 2. From here to here is 2. From here to here is 2. That's 4. 5.5. You still have some left over. That makes it 10. 5.5. Okay. So. Okay. So our L is 12 inch. This is our L. If you look at the figure 9.1 and the pitch, so that's 12. And then tangent 30, so that comes out to be 19.4 inches. So from here, we're going to go ahead and say, what thickness of plate? You, the designer, I love half-inch, because I always, when I did all those years when I worked in bridge design, I used a half-inch plate. It was my favorite. It's just biased. But you can try anything. Let's just try 3/8, almost half-inch. They make all kind of sizes, and see if it works. So now we're going to go ahead and calculate the, I'm going to come over here. This is not allowable stress design, just the one design here. Our AG comes out to be we have two plate, one on this side, one on the other side. So it's two plate. Okay, and then it's going to be multiplied by LW and the thickness. And AG equal 2 times 19.4 times 3/8. And that is 14.6 inch square. So if we go to AISC J4, page 16.145, read it. Just don't go there. Read it, see what it says. What it says, this gusset plate that we're going to put right here, and it's going to go probably here, and it's going to go around this edge, and it's going to go to this edge right there, and it's going to come back down like that. We're going to have this plate over that. There's two of them, one on each side. What is the tension capacity of this here? Can it rip apart, or is it going to make it, or not going to make it? So that's what we're trying to find out. And we're going to go ahead and from that equation, we're going to go ahead write down Rn is equal Fy times Ag, which is equal, our Fy we said it was 50 KSI times 14.6. That comes out to be 730 kips. All right, so now I'm going to go back and do my ASD here and LFRD this way. Okay, so I'm going to do both of them. So in the load resistance factor design, we had phi is equal 0.9, same area of the spec. Look at it. And then we had phi times Rn. So phi times Rn is equal 0.9 times 730, and that is 657 kip. That is the capacity of that two plate. And the tension, look at the board, and the tension that is on this member right here, it was 316. So 657 is bigger than 316. Good, we like it. And if we go on this side, omega is 1.67, and that's going to be Rn divided by omega, which is equal 730 divided by 1.67. I have 437. 437, and the capacity in ASD for that was 226, bigger than 226. So we okay here. Now we got a lot of different things with a chuck. So far, we got here, based on the number of internal force we had here, we figured out it's going to take about 10 bolts, and for both plates on each side. And then we said, okay, if we make the gusset plate 3/8" thick, is it going to be strong enough? And this is the area of the gusset plate. And we said, based on that, this area, and I found out, yes, the gusset plate is not going to rip through here. And that's what we did. But we got to do other check, like block shear rupture. So, okay, so the next thing we're going to do, we're going to check for block shear rupture of gusset plates. So you need to kind of pick it up a notch, pay attention here, and I'm going to put some writing on a screen so you can see it. We're going to go to page 16.1-146 of our manual right here. This manual right here. So now when we're going to go in that page, we're going to find out the Rn is given by this equation minus this. But what we're going to find, A and V and AGV, the gross cross-sectional area subjected to a shear, and cross-sectional area, net cross-sectional area subjected to a shear. Let's calculate those. So the average cross-sectional area that subjected to a shear is that we have two plates on both sides, and we got two lines, one line of bolt here, one line of bolt there. And then the LV is basically the edge distance of either the gusset plate or the bolt, which is we already have that as a 2". And is we got 1, 2, 3, 5, and spacing is 3 inches, and the thickness we already have the thickness. So let's do this right here. Let me just go ahead and use a different color underneath it. And AGV creates a cross-sectional area subjected to a shear. So we got two plate, and then we have two line, and then we have 2" spacing, 2" edge distance. It should be like that, plus 5 minus 1 times 3 times the thickness, and that was 3/8, if you remember. And now we're going to have about 21" square. Okay, so we're going to find the net area, which is basically, you've done this many times, the average minus the hole itself. And we have two plate, two line, 5 minus 0.5, plus diameter of the hole, this is the hole, and plus 1/16 times the thickness. So let's plug that in and see what we're going to get. We had A and V is equal 20, excuse me, (21 minus 2 times 2 times 5 minus 0.5 times diameter of the hole was 1 1/8, if you remember, plus 1/16 times 3/8. And that will give us a net area of 13" square. So this is, you can see A and V is for shear, average for shear. Now we're going to look for A and T. We have that up there, that's for tension. So net area for tension, and that is equal, let me see what I have here. I have, so we have two plate again, two plates, and that's going to be time the gauge. Let's make this bracket. See if I can spell gauge. Minus diameter of the hole plus 1/16, and then time the thickness, and let's plug that in. A and T is equal to, the gauge was 5.5, if you remember, minus diameter of the hole is 1 1/8 plus 1/16 time 3.38, and that's the thickness of the plate. So that gave us 3.23 inch square. What we're doing so far, we want to find out the block shear rupture of the gusset plate. And the AISC at this section says, well, this is the equation. For us to do this equation, we need to know this. And this is given, as you saw on this page, it tells you what that is. We need to find this, and we need to find that, all of them. So that's why we came down to this point. And we know that UBS per this page, let me write this down, UBS, and you look it up right there, per the page is equal 1. And that basically says when the tension stress is uniform on that page. And now we have that, we can calculate Rn. Let's go with color that we can see better. Okay. Rn, that shows up okay, yeah. So Rn is equal right here. I'm going to bring it back down here, and we're going to do that. And it's a 0.6 time FU is a 65. We did that beginning, remember? And time A and V came out to be 13. Okay. Plus UBS is 1. And time FU is again 65. And then time ANT, which is 3.23. Okay, what that comes out to? That comes out to be 717 kip. And should be less than this. And 717. Okay, let's find out, should be less than or equal. The bottom part, 0.6 time FOI. FOI was 50, and plus, no, time AGV, 21. 21, that's right, time 21. And then plus UBS is 1. Time FU, no, time ANT. There's something missing in the equation. Let me look at the equation again. Okay, right here, there's something missing. Let me fix this. And that is FU A and T. Okay. So it's 1 time $65. ANT was 3.23. All right, and that comes out to be 840. 840. So this is less than 840. Okay. We satisfied that. But so far we found this, but I gotta go into both, take this number, go into LFRD and allow stress design, see if it's work. So we found out Rn became 717 kips. I erased it down up here, which we said from equation J4-5, page 16.1146. And now we got to go ahead and find out this, whether in LFRD or ASD, it's going to take the block shear rupture of the gusset plate. It's going to work or doesn't work. So let's get to work. For here, for LFRD, phi was 0.75, And for AISC, omega was 2. Okay, you can see that. If you see me all the time, I look over here. I just want to explain that. I got a monitor over there, which is the video, shows the video from the camera. So I make sure I'm doing everything right. Of course, I'm talking, yeah, it's taping. So phi time Rn is equal 0.75 times 717, and that gives us 538. And the force was applied to that diagonal was 316, so bigger than 316. What does it say? The capacity for block shear rupture, if we use load resistant factor design, is 538 kips. Our load we're going to put on this is only 316 kips, so it's not going to rip. So we're going to go ahead and use allowable stress design. The reason we're using both different methods here is because some people like it this way, some people like that way. I used to love it this way, but I don't care. Both is fine. So Rn divided by omega is 717 divided by 2, and that is 359. 359. And if you go back at the beginning, the load at this right here, when we calculated, it was for PA, for diagonal, was 226. So that's bigger than 226, and we are okay. Okay, so the next phase, we're going to go ahead and look at the strength of the bolted connection for the gusset plate. Take a look at the, go to AISC edition 16 edition. This is a commentary, J3.7, page 16.1-496. In here, it says that the strength of the bolt group is taken as a sum of the strength of the individual bolt. So you find the individual bolt, and you take that, and you take the summation of that. Okay, fine. Then we're going to go into read that, what I have on the screen. Then we're going to go to table 7.1, page 721. And from page 721, look at the chart what I have on the board. And we're going to find out the individual available shear strength per bolt for 1 inch diameter, group 120, with thread not excluded. And from the shear plane, threaded condition N. And that's page 721. So we have for LFRD, let me go ahead and change color here. For LFRD, we have phi time Rn, that's from the table, is 31.8, and that is a kip per bolt. And then for the other one, for AISC, is Rn divided by omega, and that's the same table we're talking, table 7.1. We have 56, I lied, 31.8, and we got 21.2. 21.2 kip per bolt. All right, you can see that, no problem right there. All right, from AISC table 7.5, and that's page 729. And remember, our L is equal to 2 inches. We talked about that in the previous one. It says the tear out. Read that section. And what is it basically? The available bearing / tear out strength of the gusset plate at the edge of the bolt is calculated from this table here. So now we're going to go ahead and do both of them. And for ASD, it's going to be phi time Rn. And that's given from the table 84.1. Let's multiply by the thickness. And that's going to give us 31.5 per bolt, kip per bolt. And in here, it's going to be Rn divided by omega. And that is 56.1 multiplied by the thickness. Look at the table, 721. That's why it says that's the reason we multiply by the thickness. 38. And that gave us 21 kip per foot. 21 kip per bolt. Pretty similar. Okay, so if we look at the table 7-1, that is, if you look at it right here, and that is the available shear strength of bolt per kip. And then we go to table 7.5. Go ahead, go to table 7.5. And in table 7.5 on page 729, it says available bearing tear out strength of the bolt hole based on the edge distance. And then it's given kip per inch of thickness, and that's why we multiply by thickness to get the number. The reason we do that way we want to know, is it this controlling or is it this controlling? So we know this is bigger, so this is now controlling. Okay, so this table 7.5 is, let me read one more, is the available bearing tear out strength of the gusset plate at the edge bolt, this one. And we went to table 7.5. Now, what about the other one, not the edge one, the one in the middle? So we're going to go there. And to do that, we're going to go to table 7.4. So we're going to say the, I don't want to look at the reading on the board I have right there, so I don't have to use the space down here. So that's, we're going to go to table 7.4. And page 7, I don't know, 728, 727, 727, 727. Go to that page. And then we're going to use with S is equal 3-inch spacing. Let me check my camera. So we're doing good? Yeah, we're doing good. Okay, S is equal 3-inch spacing. Phi time Rn is equal 110 kip per inch. And let me look at it and see if you got that there. And time the thickness again to make it a kip per bolt. And we're going to have a 41.3 kip per bolt. And for allowable stress design, we have Rn divided by omega, and that gives us a 73.1 times 3/8 the thickness, and that will give us 27.4 per bolt. 27 per bolt. Okay. So that doesn't control. This is bigger than the other one, so this one still controls. Strength of the bolt group in the gusset plate. We talk about the gusset plate, which is over this flange here. Again, remember we did this, the tear out for the, is it going to tear out the gusset plate, is it going to tear out the flange? We're not going to do the flange because we know the flange is going to pass. By inspection, you can tell that. And we have done that in the previous examples when we did the bolting on the flange plate. So just we're going to worry about here, right here. So now let's go ahead and put everything together and see what the tear out group can do. Just look what I have on the top written. I'm gonna go ahead and use this right here, and bring back this down, and we're gonna have phi time Rn equal, we have two sides, okay, and then we have, which two plate, two lines. We know that on both sides and two lines. And remember, don't confuse this. This bolt going through the flange itself, it doesn't go all the way through the other side. But as a group, this whole strength is divided for both sides. So we got two lines, and then we have one bolt for the edge, which is two of them, but I say two lines, so that's why we have two in there. One bolt for the edge, and the edge came out to 31.5. And then we had the other four. The other four comes out plus four bolts. Four bolts come back here, time 30. 1.8, 31.8, and that comes out to 635 kip, which is bigger than 316 here. And if you do the same thing for global stress design, it will be Rn divided by omega, and that's basically 2 times 2 times 2 times 4 bolts. No, time 1, sorry, time 1, and then time 21. Then we have plus 4 times 21.2, and that will give us 423 kips, and that's bigger than 226. We okay on both sides. Great. All right, say it again. So basically, we finished this member, the tension of 316 kips, and based on all those shear and both shear, rupture, and bearing type and tear out and passed. Now we're going to move over, do the same thing with this member and that member. Okay, so now we're going to go ahead and do the top course, see how many bolts we require here, and let's go ahead and we're just going to use the same method, same procedure we used on the other one. So let's go ahead and remember, take a look at what I have on the board. So the forces over here, it become PU, basically become the combination of those two, which would be 966 minus 734, because there's two forces coming that way, and this is a continuous member, and that will give us 232 kips. And for a Lauber stress design, PA is 690 minus 524. And that will give us 166 kip. There. So now I'm going to go ahead and calculate the number of bolts required. And for the N required is equal PU divided by phi times Rn. And that was 232 divided by 17.3. And if you remember this, we did this in the previous calculation, that's 17.3. So we don't have to go through that one again. So we need about 13.4 bolts here. Now if we go to using a Lauber stress design, number of bolts required is omega times PA, divided by Rn, and that basically is 166 divided by 11.5, and this 11.5 we calculated in the previous steps, and we got 14.4 bolts here. We're going to have two lines, I don't know how many, but let's just say we have 2 lines, and we're gonna say 4. I don't like this. Go back here. 2 lines, bold on both side. We had 13.4 bold, and divide that by 2 sides times 2 row, 2 line. So 1 line, 2 line. And that will give us close to 3.35. Same thing over here. We have 14.4 divided by 4, and that should give us 3.6. So we can use 4. 4 will do, but we got a problem here. The problem is that because we have 1, 2, 3, 4, 5 here, and this plate is going to come over here. And you just cannot put 4 here and have nothing here. So the geometry of the plate is going to dictate. We know the minimum we need 4, but if we want 4, we're going to exceed the maximum spacing. The problem is, I just did those. Let me show you why. Okay. We're going to have bolts here. So I like to align up 1 here, 1 here, 1 here, 1 here. So the geometry of these gusset plate kind of dictate where we're going to put it. This is the edge of our gusset plate right there. This, let me make that line a little thicker. This is our gusset plate right here. And it's going to come in this way, and it's going to come in this way. And it's going to go up edge of right here. And then we're going to stay right close like this here, kind of like that, top of the edge. So this is our gusset plate. I wish I could have a different color so you could see it. Maybe I'll make it a dark green. One more time. All right, so that's our gusset plate. Now, because we got to line up bolt here because that's the edge. We got to maintain that 2-inch edge distance here. And we know this is pretty wide enough, so we don't have to worry about that. And then we're going to make that gauge 5.5 inch like we have over here. Then we're going to come back in here and say, okay, we got to have 2 right here at 2 inches apart. Then we're going to come back here at the edge of this right here. We'd like to put probably 1 right here and 1 right here. And then maybe line up something in between down here, and then good luck figuring out this spacing. So now we're going to use 5. The requirement is really 4. We can do it with 4. But the 4 is going to exceed the maximum spacing. You're not going to work. This is the geometry kind of takes over. And using extra bolt is not going to hurt you. Obviously, you're going to be over-designing, which is okay. But you got to make sure this plate is pretty tight. Okay, let's continue. We're going to go through all the stuff we did before. So we're going to go ahead and do the shear strength of the gusset plate. Shear strength of gusset plate. And we're going to use same thing, AISC table, page, that's a J4.2a, and that was page section 16.1-145, I think. I can't read my own handwriting. So the available shear strength for the gusset plates is, we got to go through all this stuff. Remember we did this, so let's calculate the area, gross cross-sectional area of the shear, AGV, which was 2 plate on both sides, 2 plates. Well, that's 2 plates, guys. And okay, we said 4 bolts. Let me explain this one more time. But 4 bolts not going to do it. We got to go 5 bolts because the geometry of the plates, it's going to control. We're going to have to have a 2 bolt right here. And then what is the spacing from here? We know from here to here we have 2 inches. We know from here to here we have 2 inches. We know from up to here is a 5 inch or 10 inch to here. But remember in the previous step we calculated this LW came out to be 19.4. So this came out to be from here to here, came out 19.4. So I'm going to go ahead and draw the horizontal right here. I want to know what is this distance is going to be right there, and which is basically it's going to be from center of this bolt to center of this, no, not right there, I take it back, I lied, to center of this bolt right there. Maybe the center right here, right there, right there, okay. So right here, and we knew from here to here was 19.4. And this is 11, 12, 16.28. Little math, not a big deal. So the cosine that will be 19.4 times the cosine will be this divided by that, 12 divided by 1628. Okay, 14.3. So let's just say this is a 14 inch, okay? So 14 inch, and if that means 2 times 7. So from here to here to here, 7 inch, 7 inch. So the spacing between this one and this one is 7 inch. However, there's a spec. The spec J3 from J3.5A max spacing is 24 times T, which is equal 24 times 3/8, and that'll give me 9 inches. So 7, it's okay. Now, what is the distance between these two here? So the distance between those two, so we know this angle and this angle based on here. So this, it's going to be, from here, it's going to be 42.5 degree. We don't know this, we know that. This is half of 14.5, which is 7.3. So if we're going to say tangent of 42.5 is equal the opposite, which is a 7.3 divided by, we don't know, that x should come out to be 8 and a change, 8.1 something. So I can say, all right, this distance right here, let's make it a 8.25, go to the nearest increment. So now we got 8.25, and you got 14 inches, and another 2 inches, and another, and this is 2.5 divided by 2. You can figure it out. It's simple math anyway. So we have all that information. Let me erase this so we can continue with this thing. So now our L from here to here, it's going to become 14 plus 2 inches this distance plus 8.25. That's 24.25. And then I have from there half of the gauge, which is 5.5 times 0.5, 27, and plus 5, 32. So that comes out to 32. You can do a quick math. 14 plus 2 plus 8.25 plus half of the gauge is half of 5.5 and plus 5, it comes out to 32. So this number comes out to be 2 times 32 times 38, and that took a long time to get that, and that comes out to square. From J 4.3, you can look off the page, we already went through that. Our Rn is equal to 6 Fy times AGV, and that become Rn is equal to 0.6 times 5024, 720 kip. Finally. Now we can go ahead and say, okay, low resistance factor design, RFD and ASD. Okay, we can use those two, and that's going to be phi is equal 1 for here, and phi times Rn is equal to 1 times 720, and that's a 720 kip. And our 720 kip is a lot bigger than the force came out to be 232. And then here for omega is equal 1.5, and Rn divided by omega is equal 720 divided by 1.5, and that is 480, which is bigger than 166. Okay, now we're going to go back. We have all this laid out. We're going to check for the shear rupture. Going to AISC J42B, section 16.1, page 146. We can calculate the net shear area, which is 2 plate L minus N. And our L was 32, 5 bolts, blah, 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 and come out to 19.5 inch square. Then our Rn, comes out, the available comes out 761 kips. Now we have that. We're going to go to LFRD and ASD, and from the same area, phi is equal to 0.75, and therefore phi times Rn is equal to 0.75 times 761, and that is equal 571, which is bigger than 232, if you remember that, the number for that. And going on the other side, omega is equal 2, and therefore Rn divided by be 761 divided by 2, and that's give us 381. 381, which is bigger than this came out to 166 kip, and so we okay on both count. And we know from before that we did the strength of the bolt connection, And we did calculate that based on this, the bolt connection is not in control, so we stay with this, and we can basically go ahead and move on to the vertical member. So let's go to the vertical member. And be in this one right here. And again, we're going to calculate PU. And PU was 286 kip, remember? And then and PA for this one was vertical member, VM vertical member. PA was, we calculated that before, was 204 kips. So the required number of bolt, N required, and it's going to be PU divided by phi time Rn, which is 286 divided by 571. No, what am I thinking? We calculated it was previous step 17.3 kips per bolt, remember? And that gave us about 16.5 bolts. And on this side, it's going to be same thing. N required is equal 204 divided by, remember, 11.5. And that gave us a 17.7 bolts. Going for, again, for 2 lines, 2 sides. Two lines, 2 sides, just like before. So we're going to have 16.5 divided by 2 times 2, and that will give us a 4.12. And here we have 17.7 divided by 4, same thing over there. It gives us 4.43. We're going to use 5 bolts again, and with a 3-inch spacing. So we're going to have one, they're going to basically, it's going to line up right here. I want the center of these bolts. So we're going to have one here, and then do the same thing. 1, 2, 3, 4, 5, tie your shoe, and then we can have the flange, how far it has to be from there, because of the 2-inch spacing from there. So let's check for shear strength. Just like we did the first, I'm not going to explain it. We're going through the same thing, and that's going to be from a J4.2A. Go back to page 16.1-146. We got to calculate the area of average area of the shear, and that was 2 plate, okay, time L time T. Oh, our good L. Did a lot of mathematics. So the L for here from to here is going to be a 31. Just since we know all this from here to here, we know this diagonal, we know this length. If that's a 32 times 11 and 12, same thing. It's almost 32. So we call it here 31 and 3/4. So time 2 times 31.75 times 3/8. And that gives us 23.8. 23.8 inch square. And based on that, again, our Rn is equal 0.6 for sure is the Fy time AGV, 0.6 times 50 times 23.8, and that is equal 714 kips. So now I have that. So we're going to go ahead and do LFRD and ASD, and we got phi is equal 1 for here. So our Rn stays the same, and we're going to say Rn is equal 714 times 1, which is equal to 714, and that's bigger than 286. Okay, and this side is going to be Rn divided by omega, and omega is 1.5. 714 divided by 1.5, and that's 476. And that is bigger than 204. Way over. We're going to go ahead and calculate the same thing over here, A and V. I'm not going to write the formula down so you know. A and V, I need space here. So A and V for this vertical member, it's going to be 2 times, we already figured out the distance, remember, so from before, that's a 2 plate, time 31 and 3/4, 0.75, minus, here's, pay attention here, it's 2 times 2 plate L minus N. L is 31.5, but N is 1, 2, 3, 4, 5, 6, 7 on that line. So it's going to be 7 times 7 times 1 1/8 and plus 1/16, and then time T, which is 3/8. And that will give us 17.6 inch square. And our Rn, it's going to become, again, this is not the ASD, just continuous. So I'm going to erase the line here. Our Rn become, for this kind of 0.6, I think it's a FU, yeah it is. FU times A and V, which is 0.6 times 65 times 17.6, and that is equal 686. Okay, so now we have that. We're doing the same exact thing, and we're gonna, phi is equal 0.75. Let me finalize this with this color. I don't know what to do with it. So phi is equal 0.75, and our Rn is time phi is equal 0.75 times 686, and that is equal 515, which is bigger than 286. This side, omega is equal to, for ASD, omega is equal to our Rn divided by omega is equal 686 divided by 2, and that is 343, bigger than 204. We don't have to check the other stuff because we already checked it through here, the group tearing and all that stuff. So this was the critical part of it. And just take a look what I have on the board. this was kind of tedious, and the final, your Gusset plate look like this. You work with the detailer, and you can figure all this stuff out. They're pretty good. They usually lay it out in a paper or the computer program and give you all these geometry shapes. I know this was a long one. I hope you liked it. I love your comment or thumbs up. Be good. Tell me I'm doing a good job. Take care. Have a good day.